Okay. All right, here we go. Okay, so let me draw this properly just to make sure I get it right. Okay, all right. So I think this is good. So let me put the origin right here. Positive Q is at negative A. That's negative A. You have a positive Q there. There you go. All right. And positive 3A here. Okay. Negative A, positive 3A. You have another charge here. Okay. The net electric field, these charges produced at the origin, it has a magnitude. They just only know the magnitude here. Electric field right here has a magnitude of 2kq over a square. All right. So what are the two possible values of the unknown charges? So because you know the magnitude at this point, so that means I think there are two directions that's possible. Okay. And am I missing anything else? Okay. Unknown and the net field. Okay, I don't think I missed anything. All right. Okay. So, okay, one thing that we can do, wow, isn't that, I don't know, overthink about this too much or not, but let's imagine first what is happening to the Q. Of course, that positive Q will generate the magnetic field at this point. Let me call this E1. It's always point to the right, that's for sure. So the magnitude of the E1 is going to be K big Q over A square. All right. And if I put it in a vector form, it's going to be in the positive I hat. So it means in the positive X direction. Sounds good? All right. Now, so what you have left to do is now it turns out that the net electric field at the origin has a magnitude of this. Is 2, which is twice as big as the one that you're having right now. You see that? Okay. So one possibility is there must be an electric field that helps enhance this or increase this by the same amount. And that must be come from, okay, I should actually put on the side like this so it won't get confused here. So you hope that the electric field due to that green unknown charge will generate the same magnitude as this one in the same direction. So you assume that this, let me call this E2 first, supposed to have exact same value and pointing in the same direction for you to have a final net charge to be exactly 2kq over a square. Is that good? Or another possibility is that green can generate the electric field that actually twice as big as the E1. However, point completely opposite to the E1. So you might have this all the way here. Does that make sense to you? So if this is the case, then the black vector will cancel out the red one, and eventually you end up with twice as big as the original. So that means to make it sort of like drawn two scales, this has to actually go pretty far. Okay. Once you cancel out with the red, then you get 2kq over a square back. So that means this one's supposed to have 3kq over a square. Does that make sense to you now? All right, so that's why you have two cases possible. So one, the E2 case, this one, that unknown Q, let me call it like Q prime at this point, must be negative. Okay, and for the second case, let me call Q double prime, it must be positive because you want it to point away from this. So let me try, the first one, what kind of Q prime you need. So let me put prime in here. Oops, sorry. So you want this, right? You want KQ over A squared as a result from the Q prime that's you want to figure out. So electric field due to the Q prime is going to be KQ prime over 3A. That's a distance square. Does that make sense? That is the electric field generated by the Q prime charge. But then you said you want this magnitude to be exactly this much. So you just put it there. So you just say it's going to be KQ over A squared. And that lead you to, okay, K cancel. So the Q prime is going to be, what is that, 9Q. There you go. A square cancel as well. There you go. That's the first case. And the second case, you do the same thing. Electric field due to the charge number 2. Let me call E2. Let me put double prime there. My notation is really bad at this point. So, all right. So let me, it's still E2 anyway. So it's still E2. But now the magnitude of E2 in the Q double prime case is going to be K Q double prime over 3A square here must be equal to, now you want this much to put in here. So it's going to be 3KQ over A square. And that give Q double prime to be 27Q. There you go. But it's supposed to be positive in this case. So you put positive sign there. And it's supposed to be negative in the first case. So it's going to be negative Q, 9Q. And I think that matches with the answer given, I think. All right, so good. All right, done. Next. Okay. Let's move on to homework set 8. All right, so in the set 8, you guys have only 4 and 6, and the rest are just 9 and 10. Okay, so let's look at homework 8, number 4. Okay, so this one is 7-4 problem. Okay, there you go. All right, so let's take a look at 8-4. So the sound is, it's getting better now. I mean, at least not better, I mean, normal.
Normal.
Okay, all right. So maybe it's just process a lot of stuff there. Okay. 8-3, 8-4. Okay, 8-3 as well. Okay, very good. All right, so let's look at 8-3 first then, and then we move on to the 8-4. Oh my God. I'm going to have to deal with this computer this afternoon, get it done. All right, let's start with 8-3. You have 3, 8-3. All right, so you have 4 charges located at the corners of a rectangle shape, sort of, distribution here. Calculate the energy required to assemble the array of charges shown in the figure. All right, I love this one. Actually, I think this is the hit. I'm planning to put this type of question in the exam anyway. So this is very good. All right, so what you have over here is you have okay, let me put a location on first. Okay, so you have, it's not a square. Okay. All right, so you have the length B, the width A, and then we have charge lying around. Okay, let me sort of redraw everything on here so we can explain everything on this screen here. All right, here we go. So it's Q minus 2Q, 2Q, 3Q. All right, so I think if you get this, concepts of these problems, then I think the rest will be quite okay. All right, so to be able to construct this whole setup over here, the question asks you how much energy it's required, right? So first thing first, you have to imagine that to construct this structure of charges here, first you have to bring in the first charge. You can bring in any way you like. For example, you can start from the upper left corner charge. So you start bringing in this one right here. Yeah, let me sort of put there. But bringing in the first one is a free one because there are no other charges around. So it won't feel any electric field. It won't feel any electric force. It won't feel any electric potential. So it's been bringing in the charge Q here in the first place doesn't cost you anything. It doesn't cost anything because you can just move to that charge and then call it this is a starting position, right? Something like that. Okay, now bring in the second one. Let me bring in the negative 2q here. Okay, so now here comes the question, how much energy is required to bring in the second charge, which is a negative 2q here? The answer is you just have to ask yourself what is the potential at that corner. So just to be able to communicate, let me call these corners like A, B, C, and D. Okay. So what is the potential at point P? I would say V at B is going to be K Q due to the upper left corner charge at corner A over B. You guys with me? All right, but we discussed this in our lecture that actually is not like a totally like a hanging alone V sub B. It's actually is a V sub B relative to infinite distance charge. All right, so it's mean it's just like KQ over B subtract 0, something like that. But at least what you're saying over here is now you know what is the potential at point B. And now you have to drag that 2Q negative from infinity to that point. How much energy is required? So the energy that's required is going to be, okay, let me put this, energy that required to bring in the negative 2Q charge is going to be the charge itself times the delta V. You guys with me? This is a standard problem, standard expression to calculate energy. So what you have to do is just taking the negative 2Q, that is the amount of charge. If I want you, I mean, I don't want you to get confused. Let me use the capital Q for this to distinguish, yeah, the actual charge that we're going to use. Okay, so the charge that you're bringing in is negative 2Q. You're dragging from infinity, which is 0 potential, to point B, which has the potential of KQ over B. So you just have to multiply by this. So the energy required is going to be KQ minus 2Q over B. Done. Okay, you guys? Is it good? All right. Now that's done. That's the first one done. Now let's move on. I'm going to bring in the third charge. Let me bring in this one right here, corner D. Okay. For you to bring the charge from infinity to this charge, the only question that you have to ask, I mean to ask and answer is what is the potential at point D? Okay. And then the potential at point D is going to be, now you have two charges waiting for the charge at point D. So the potential at point D at this point is going to be KQ over B. That's coming from this pair. With me? Okay. Plus K minus 2Q over the diagonal right here. Okay. So it's going to be A squared plus B squared square root. There you go. And now you're taking the 2Q charge, this charge right here, from infinity to this point. So the energy that required for you to bring in the 2Q charge is going to be the 2Q itself times the delta V from D. I mean, I can call it from infinity to point D. Does that make sense? If I'm writing like this, just to confirm that, hey, you want to drag that 2Q charge from infinity to corner D. And that is 2Q times the whole thing that you just put there. Just calculate it, KQ over B plus K minus 2Q over square root stuff. Okay. Does that help overall? All right. But anyway, now you start to see that the amount of energy required is going to be, okay, carefully look at this one. I know my writing is kind of bad at this point. What about charge? Okay, we'll wait for that. That's the final step. So now you see that there's a 2Q here with the Q. That's 2Q here with the Q. And then you have 2Q here with the negative 2Q. 2q here with the negative 2q. You guys with me? So there is another pair there. And the first one that you calculated, you have q with the negative 2q. You have q with the negative 2q. I'm just trying to do the color coded here, right? But what you are seeing over here, it seems like you are having all the pairs in this setup start to form the whole final conclusion here. You guys with me? All right, so let me do the last one. It's going to be the biggest one. So I'm going to bring in the fourth charge here, which is 3q. So now you start to see what will happen. You first have to have to calculate what is going to be potential at point C, right? So I'm going to have to find the V at C first. Okay, let me don't write it down yet. But at least you know that the V at point C will come from this pair right here. When I say this pair, don't have to think about pair yet. But let's say at point C, there will be a contribution of the potential from that 2q charge. And there will be a contribution from the q charge. And there will be a contribution of the negative 2q charge. Yes. All right. So that means for this V at C, you're going to have three terms. K 2q over B, that's starting from here, plus KQ over the diagonal, that's from here, square root, plus K minus 2Q over A, that's from this. You guys with me now? So you have three terms. And then when you want to calculate the energy, that bringing in the 3Q here, what you take is you bring the 3Q, and then you times the whole thing again. Let me put this whole thing in the brackets. There. I'm going to bring in the bracket right there. Here. Okay. And now you start to see that, oh, Ajahn, you're going to have to pair up again. See this? It's going to be Q multiplied by the 2Q. It's a Q multiplied by the 2Q. Sorry. Wait. Yeah. Q multiplied by the 2Q. It's right here. Woo. 3Q. Sorry. 2. Wow. Where did I start? My bad. Sorry. Okay. 3Q pair with the 2Q. Okay. 3Q pair with the 2Q. There. And then that 3Q will pair with the Q. 3Q pair with the Q. And I don't know, am I explaining this well or not? And the 3Q that is paired with the negative 2Q right here. 3 layer. Woo. All right. So at the end, what you're getting is you're going to have total of, see this? You have, got 1, 1, 2, 3, 4, 5, 6 pairs. That in the form of the K times the pair of the charges and the distance between them. And that's how you can pair up 4 charges here. Because if you count the number of ways that you can pair these two together among these 4, you're going to be like A with the B, A with the C, A with the D, B with the D, B with the Z, and that's 6 ways, 6 pairs. And that will be the total that you're going to get. Oh my God, it seems like my explanation is bad. Is it good? Does that make sense to you guys? You guys look so quiet. Cloudy. Not good then. That is not very good. All right. You want me to start again? Or for majority of you guys seem to get what I'm doing over here. I think maybe my drawing is bad. I shouldn't start with the whole image. I should start from nothing first. So what about the rest of you guys? Okay, you want me to start again? Just overview what we are trying to do. Okay, let me do again. Do again. Oh, that's my bad. I think the space that I'm drawing is not good. Can we just All right, I should like, I need more space here. It's supposed to fill up the whole thing. Zoom in and then draw. Yeah, I'm doing it right now. All right, then try again. So the way that I'm going to construct the whole structure is first bringing in the first charge. That's Q. Cost you nothing. There's no energy required. So now I'm going to bring in the second one. So let me, I think I try to color code it here, right here. Okay. So over here, the charge that you're bringing in is negative 2Q. So now the question is, how much energy you need? First, you have to ask, what is the potential at this point, which we name it point B, right? That's A, B, that's point B. So potential at B is K Q over B. So the energy that required, the energy to bring in that negative 2Q here is going to be that charge negative 2Q times the potential itself, K Q over B. No power of 2, no. Potential is only power of 1. All right, so that's the first amount of energy that you need to bring in that negative 2Q to point B. All right, I'm just gonna give you some, change of the mood a little bit here. Now I'm gonna bring in the third one. That's a corner C, okay? And the third one has the charge of 3Q, positive 3Q. So first thing first, you have to find out what is the potential at point C. Potential at point C is first here. Think of it this way. So it must be the potential due to the charge Q. So it's going to be K Q over, let me call this R for now, just make it easier to write. Okay, but R is just the Pythagorean from, A and B and all this stuff. Plus K. Now there will be contribution from that negative 2Q charge as well. Does that make sense? All right, so you have K negative 2Q over the distance, which is only A in this case. Let me put like a black one here. There you go. So the energy required for you to bring in the third charge plus 3Q is going to be that positive 3Q. That's a charge multiplied by the potential at that point. And it's going to be K Q over R plus K negative 2Q over A. All right. Now the last one, I want to bring in the fourth charge right here. There you go. All right. And the fourth charge over here is 2Q positive. 2Q. Let me call this point D. Potential at point D, it's going to be K. Let's start from the first one. You're going to get some contribution from this. And that's going to be Q over A. With me? Okay. Plus, you get some contribution from there. Okay. And that is going to be K negative 2Q over R. Plus, you still have one more. Here you go. That 3Q is waiting for you as well. So it's going to be plus K 3Q over B. Yes, does that looks better? I don't know. I hope it's better. All right, here we go. A. And that's it. It's the energy required to bring in the fourth charge here is going to be the charge multiplied by the whole V. K Q over A plus K minus 2Q over R plus K 3Q over B. And that's it. Done. The total energy required is going to be E minus 2Q plus E plus 3Q plus E plus 2Q right there. I can call it possible. Done. Woo. Looks clearly. Thank you. It's my bad. Clear as one. All right. So, but the point that I was trying to make is this. If you look at the total summation over here, you will see that in the first expression over here, you have here, let me draw this. See Q and the Q here. I'm sorry, 2Q and the Q here. That is this pair right here. See? All right. And in the second expression, you have this 3Q that is pairing with the Q and the negative 2Q. So you have two pairs out of this. So look at this. Here, plus 3Q is this corner, and it's going to pair with the Q, and it's going to pair with this minus 2Q. This look colorful now. And then the last one, you can see that it's a 2Q that is pairing with the Q, pairing with the minus 2Q, and the pairing with the 3Q. So you're going to get this connection here, 2Q to the Q, 2Q to the minus 2Q, and 2Q to the plus 3Q. See, it's like playing games here. So what you're having actually, all you need is just the sum of all of the pairs that has the form that looks like K, the pair of the charges, Q1 and Q2, divided by the distance between them. That's what I'm having to show you right here. So I think I should draw something like this to look like a pair. What happens if the total is negative? That's fine. The total is negative means this system is actually prefer to stay together. That means the total energy is actually lower than zero. So it will prefer to stick together as a shape like this. And if the net energy is positive, means it requires you to input some energy to it to build this structure. So it seems like they're not going to try to assemble themselves into this structure by themselves. I mean, you need some extra energy to do it, something like that. Does that make sense? Okay, okay, all right. So actually, this is exactly what you saw maybe in chemistry. When you want to build a compound structure, you know, you have like some molecules, you want to build something out of it, then you need some energy. But okay, it's more complicated than just regular charge distribution or this stuff. But the idea is there that, I mean, there must be some energy required for you to assemble something. Yeah. So that's the energy that is, I can say it's built into this structure. So let's say if this structure is positive, and if somehow you can make a chemical reaction that can dissociate these structures, sort of like tear them apart or something like that, it will have some energy released from the structure. And that's how you get some chemical energy out of this stuff, for example. Does that sort of make sense a little bit? Yeah. Okay. Okay. All right. All right, but I mean, in the real story, it's going to be more complicated than that, because after, you know, building a like a molecules and other stuff, then you have like, you know, bonding, and then you have a relocation of the electrons, other stuff. So it's not just like having charges lying around. You have some internal electronic structure that is also changing. All right, but at least this is what it is. Whew. Okay, sorry for the first explanation. Is it my drawing is bad, so this is not good. All right, this one seems to be a little bit better. All right, next, move on. Yeah, it's lacking. I can even see the screen doesn't really changing. I already changed the page a long time ago. Okay, next, 8.4. Okay, very good. All right, this is sort of like a calculus-based problem. Okay, even though, well, I hope to not to go too far from what we are doing in the class, but this is because this is like a homework question, so I want to challenge a little bit. But in the final exam, don't worry, it won't be like, way too difficult or anything. A wire having a uniform linear charge density is bent into a shape of like a half circle, and find the electric potential at point O. All right, guys, so let's do this. But you are okay with this to be like a question in the final? Maybe, or maybe not, but maybe this is already too much. Okay. All right. So how did you do with this one? All right, you have 2R here. That's 2R. That's R right there. And that's 2R again. Okay. And the charge density is lambda. So that's a charge per unit length. All right, first thing first, let's attack the easy one first, shall we? Let's look at what is going on from this half circle arc. What would be the potential that this arc contributes at the origin? Yeah, the answer is pretty good. I mean, you can start from the calculus if you like. You can slide this into a tiny piece, chop chop, and then this tiny piece will contain a tiny charge dq. And the distance of this dq to the point of calculation is r. So the mini potential that you're generating is going to be k dq over r. That's good, not bad. And then now you want them all, so that means you just have to do the summation. You start slicing from the left end to the right end, or the right end to the left end, depends on your coordinates. Okay, right there. All right. And once you're done with that, you're going to end up with the total potential. Let me call this V1 then. This is like the first part of the thing that we want to calculate. And that is going to be K. R is constant. I can pull it out. You don't need to do any integration here because the total charge on this half circle arc is going to be just lambda multiplied by pi r. You guys with me? Is that easy enough? You want the charge, you take the lambda multiplied by the length. The length of a half circle is pi r. So the amount of charge on here is going to be lambda pi r. The reason this is easy because this is exactly what we did in class. Whenever you have charges at same distance, you can actually sum all those charges that are located at that distance together. And then you do the KQ over R and then you're done. All right, so this portion of the calculation is not bad. Now let's try and move on to the next. What about the straight line portion over here? The good thing about this problem is it's symmetric, left and right. So that means if you can figure out the potential due to the left, that blue highlighted straight line portion of this charge, it's going to be exactly the same potential that coming from the green parts because they are exactly the same. Okay, does that make sense? So let me do that. Let me name this potential to be contribution from this one to be V2 then. All right, you do the same thing. You do the slicing, chop, chop. It's contain the charge dq here. Or actually, why don't we do on the right side? And it's going to look exactly as the left. So let me do the one on the right. Sorry, let me call this. There you go. All right, it's going to contain the charge dq right there. All right, just to make it nice and neat, you just have to set up a coordinate so you can work on this one nicely. So we use the same trick as we did before. So we just put this into a origin, yeah, and then you just have this whole charge lying on an x-axis right there. Okay, pretty good. All right, so it's the same problem that we did in class. You have a rod that have the left ends of the rod sitting at the distance x equal to r, and then the rod itself extended from that 2r away from the left end of the rod. So that's not too bad. So let's do it. So it's going to be sum of that mini potential due to that charge dq there. Okay, very good. So far, so good. And it's going to be k, that mini charge divided by x. Because you already set up this onto an x-axis, so the position of the dq is already x variable. Pretty good. Keep going. K is constant. I can pull it out. X cannot be pulled out because X varies. That's a variable. dq is not in the form of the dx, so you need to transform that into something of x. So we use the lambda dx. Here we go. Take that into account. Looks good. All right, because lambda is also constant, I can pull that lambda out. And the integral of 1 over x that left in there will give you log of x. And then you do the integration from where? Of course, I'm going to start from this end of the rod all the way to the right end of the rod. So I started integration from x equal to r and ends my integration when x equal to 3r. So that give us the lower limit and upper limit of integration right there. Cool. And that give you the lambda k log 3r, subtract log of r. So it's log 3r over r. So it's log 3. And that's contribution from the right side of the rod. And this going to give you exactly the same as the left side contribution from that straight line because they look exactly the same. So it's going to be the same as the V2. Okay. And that's it, guys. The total potential at the origin is going to be V1 plus V2 plus V3. And it's going to be whatever you got right there. Done. Woohoo. Is it sort of like qualified to be problems in the exam? I think it's not bad. It's quite doable. All right, cool. Next is 8-6. Okay, and maybe the 6, that's the problem. Really good. Maybe it's getting worse. All right, any question on this one? Looks okay. So this one seems to be good. All right, now let's attack problem 6. Do you have a rod of length L lying along the x-axis? And it has a non-uniform charge. This density. Whoa. Oh, I can see. I think there is a missing equation here on the problem 6. Whoa. Whoa. Yeah. Okay, I can see why you guys having question on this one. Yeah, you don't have that expression there. All right. But anyway, this one, I would say maybe it's too much for the exam because I mean, this is like an ultimate one in the sense that you need like Pythagorean theorem plus, integral. That looks really bad. So I think you guys can let go of this one. I think you should be okay. I think you just focus on the problem 4 and 5. I think that's more than enough. The 6 is only complicated due to the geometry of the problem. You sort of like go off the axis and then you try to calculate the potential there, right? So that make it, it's mathematical complications, not the physics problems. Okay, guys. So I hope that answer your problems. Okay. All right. So that's that was a good question there about the energy calculation by doing the potential calculation first and then bring the charge one by one to build a structure. That is a very good question that I like. And the second one is, of course, the basic, integral problems that you should be able to do. Okay, at least the electric field and electric potential from a continuous charge distribution. All right, so you sort of ask good question here. All right, next. So let me move on to problem set 9. Okay, how many questions you have? You have number 3, number 7, and number 4. Okay, so we're going to attack 3, 4, and 7 in the set 9. Okay, here you go. Okay, let's start from number 3 first. Okay, number 3, they ask you to calculate the total electric flux. This one, I love it as well. All right, the reason is there because that's the clue what will happen in the final. Calculate the total electric flux. A, paraboloidal surface, so that's the curved surface on the right, and B, the entire closed surface due to a uniform electric field magnitude E0 from left to right. Okay, guys. So number 3, we use the same technique that we established, saying that the flux calculation came from E dot with the area vector that we built. And the area vector, I think everyone now familiar with, is it's the vector that you generated by having the vector sticking out from the actual surface. Yeah, does that make sense? All right. So that means every time that electric field light up with the A, that's by the dot product. That is a current guarantee that the electric field is actually piercing through that A perpendicularly. So that's very good. Right, so that was like a quick review right there. Okay, so you can write this one in terms of the angle between the two vector. That is also fine. But the key concept about this one is it's about the projection. So that means every time that you have an electric field pointing in one direction, the area that you care to take into account is just the area that is oriented perpendicular to this electric field. Does that make sense? You don't care about the surface that is parallel to this. So that means if the area look like this, no, you don't want that one. You want the one that actually gonna fall perpendicular. Okay, the actual area has to be oriented perpendicular to the electric field to guarantee that dot product. And that allow you to saying that if the actual surface is curved or whatever, I don't care. As long as the component of the area that is perpendicular to the electric field is being taken into account. That's all I care about. Okay. So that's why I said in class that you can imagine like you shine a light in the direction of the electric field. That's my flashlight right there. All right. And you just ask that what kind of shape of the shadow that surface casting on a screen that is perpendicular to the electric field. Does that make sense? All right. So because right now you have like a bullet shaped surface like that, and the electric field is already points in this direction. This is good. So you can imagine like, hey, if I shine a light here, what kind of shadow you're going to get out of this? You say, oh, John, I'm going to get a shadow that looks like a circle on a screen that I put perpendicular to the field. Does that make sense? And that's it. So that's make this problem quite all right. So the flux will enter the left surface of this one, no problem. This is an influx. And that paraboloidal surface on the right eventually will only cast a circle of the same size in the shape of a circle with the same surface area as the green surface. Same area. Very good. So this is going to be an out flux. So this is in flux here. All right. And this is going to be out. Coming out flux. All right. So that's good. So if you sort of okay with this review, then let's go back and attack the problem. They just want to figure out the paraboloidal surface, how much flux on it. You say, but oh, okay, no problem. So flux on that paraboloid, let me just shorten it into para, and it's going to be just E dot A of that paraboloidal portion of this one. Okay, however, overall, it's just going to be E times A of the, let me put it like a shadow. Okay, is that good? All right, this A of the shadow. And that is going to be, it's going to be positive too. You guys with me? Because we only care about the right side of this shape over here. So the area vector is going to point in this direction right there. That's a para. Okay. That is already perpendicular. So let me put it like this. So just to make sure that I only care about the perpendicular component of the A paraboloidal surface. There you go. All right, so it's positive right there. This is good. And that's it. It's going to be positive E times pi r squared. I'm done. That's it. Okay, and what about the entire closed surface? Let me call it the sigma. It's going to be the flux through the left plus flux through that paraboloidal portion over there. And now you can guess. Yeah, it's supposed to be 0. This coming from here. Cool. Let's drop something. Here we go. Brain explode. It's not too bad, I hope. Is that still understandable, I think? Yeah, so once again, just want to make sure that I mean, using the same analogy that we did in class, right? If I have electric field piercing through my head right now, okay? I want to know how much electric flux going to my face. All I care about is I just have to, cast the light onto my face and look at behind me. If I have a screen behind my back over here, look at the shadow of my head. The amount of flux going through my face is going to be electric field multiplied by the area of my shadow. That's all I care about. You don't have to care about my nose. You don't care about my forehead and everything. No matter how curved it is, the area that you want to take care of is just the one that is fall perpendicularly to the electric field. That's all you care about. So that's why you only care about the surface of my shadow. Yeah. That is the dot product at work right here. That's good. All right, guys. So is this good? All right. So this is, once again, you asked the right question. This is a good hit, actually. It's definitely is going to be this question in the exam. Not exactly like this, but about flux calculation. All right. Next is going to be 9-4, if I right. And I didn't skip anything, I hope. All right. So it's going to be 9-3, 9-4. Oh, no. All right. 9-4, 9-7. Okay. All right. 4 and 7. You have a solid sphere. Okay, so let's do, go. A solid plastic sphere of radius given 10 centimeter with a charge with uniform density throughout its volume. Okay, very good. So you have a sphere. Okay, maybe it's too small here. There you go. All right. Okay. Now, the electric field of 5 centimeters from the center is given, okay, radially inward. Whoa. Find the magnitude of the electric field 15 centimeters from the center. All right. How did you do this? Oh, actually, this is a very good question, guys. All right. So you have the reason they put a plastic sphere because they want to be like a non-conducting material, right? So that's mean you can spread around the charge throughout the sphere, and it's a solid piece. So it means it's like the full solid stuff, plastic. All right, the whole surface, the radius of this whole thing is 10 centimeter. All right, let me put 0.1 there. Okay, there you go. Uniform charge density. Why don't we just call it rho for now, right? It's just fixed value of the charge density per volume. Now the electric field at 5 centimeter away, so it's halfway from the center, is given. So it's mean once you standing at halfway, I mean the distance, radius wise, right there. Oh, that's bad looking. Okay, here we go. The electric field is already given. So let me name this electric field at this point to be E1. Half, yeah, halfway, right? E half is given to be 86 kilonewton per coulomb. And it's radially inward. So it's I mean, that is the clue saying that electric field is pointing in. So we're supposed to have like a negative charge in there. All right, but that's all right. Find the magnitude of the electric field 15 centimeters from the center. So they want you to figure out what is going on here at 15 centimeters. Now, it's the Coulomb's, or not Coulomb, sorry. It's a Gauss's law in action right here. Okay. So slowly, starting from the first information first, if you're looking at E half, E1 half right there, how you calculate that one, you can start calculating this from E half equal to K, the charge inside. Remember, we already agreed when we did this Gauss's law 5 times. As long as you have a charge in the form of a spherical distribution, okay, no matter where you are, no matter what you do, it still looks like a Coulomb's law. It's a KQ over R squared. Does that sound good? All right, no matter it's a dot, no matter it's a shell, no matter it's a solid piece, as long as you are interested in stuff that is away from it. So everything looks to be in the form or in the shape of the Coulomb's law. So that means it's going to be K with the Q. Let me call Q inside. So it's included charge just only inside that green highlighted area over there, divided by the distance, which is right now is only half square. You guys with me? Okay. However, now, what about this Q included over here? Even though you don't know exactly how much is this, but because we express everything in terms of the rho, so I know I can express this one as the density multiplied by the volume of this green scoop. Remember, like we have like a blue one is like a big ice cream scoop over here, and the green one is a smaller one there. So if I want to know the amount of ice cream that I'm going to get, I just take the density multiplied by the volume of that mini scoop in there. So it's going to be 4/3 pi the radius cubed. There you go. All right, so that means the information that you have over here allow you to calculate the rho, the density, the charge density is already given in this first equation right here. Does it sort of like feel better now? So now you turn your attention to what is going on at 15 centimeter. So let me highlight the red one. Okay, so E at 15 centimeter. So let me call it 15 centimeter. So here we go. So electric field at 0.15 meter from the center. It will look the same, K, the charge that is included here. So let me put prime in it so it won't exactly the same as the Q included up top. And then you divide it by the distance over here is going to be, wait, they want it at 15 or what? Am I right? Oh, 15. All right. So it's already outside, guys. Sorry, my bad. Okay. My bad. So 15 is already outside. Sorry, guys. Okay, let me draw this one more time. Okay, that's my mini cycle there. Okay, now the 15 is out here, guys. All right, you guys didn't complain, so maybe I lost you somehow. I don't have sound effect today. Okay, all right, guys, sorry again. So, but anyway, so it's still within the same stuff that we did. As long as it's spherical shape, electric field due to the Gauss's law give you back the Coulomb's law expression. So over here, when you are already at 0.15, so it's already outside. Okay, so the electric field will be K, the charge included, divided by 0.15 squared. Cool? All right. And now, how much charge is included here? Of course, because the charge is only go up to the radius of the ball itself. It won't go beyond that. So that means this amount of charge is going to be the same rho that you already found out from equation number one. Equation number one allow you to figure out the rho. And then you do the 4 pi of 4/3 pi, the whole radius cube. And that's it, you're done. Cool? All right. So actually, if you don't like to calculate the rho, you can just take equation number 1 and then you can call this equation number 2, and then you can divide these two out, and then you can cancel all the rho and everything. You only have to compare about the radius if you want to. Pretty good. I hope this works a bit. Not too bad. Okay, very good. All right, no question means okay. All right. Next, it's going to be 7. All right. Number 7, you have, okay. Just let me know if you have question, yeah? If not, then I'll just keep going. Number 7, a hollow conducting sphere is surrounded by a larger concentric spherical conducting shell. All right. You hit a good question again, guys. All right. So the application will be around this circle stuff here. You have a hollow conducting sphere. Okay, let me draw like a big one here. Okay. And it's surrounded by a larger concentric sphere. So it means I need 2 concentric sphere. Okay, let me put them. Oh, whoa, what happened here? Okay, here you go. Pretty good. All right. Now, the inner sphere has a charge negative Q. All right, so you just put negative Q here. And the outer shell has the net charge of positive 3Q there. The charges are in electrostatic equilibrium. That's what we, only thing that we did. Right? We don't know what happens if it's non-static. Using Gauss's law, find the charges and electric field everywhere. That's like a super wide question. All right, but anyway, let's start from the easiest one, guys. What if you are standing outside? So it means you are already far away from these 2 concentric sphere. So that means, let's say you're standing out here, super far away. Okay. So what you have for the expression for this one is just saying that from Gauss's law, total flux is equal to integral E dot ds. Yeah, this is just a review, and it's just the charge included inside over epsilon naught. That's it. Okay. But because we already confirmed from the previous examples and the rest of the examples that we did in class that as long as it looks like a sphere, Gauss's law will lead you back to the Coulomb's law expression. So I can just say electric field over here, let me call E outside. Electric field outside will be equal to K, the charge inside this big green sphere over here. So it's going to be plus 3Q minus Q. You guys with me? Divided by the distance square. And if you name this R, then you're done. Okay, so the electric field, as long as you stay outside, it will have the magnitude of the K times the 2Q over R squared, and you're done. Okay, and now you start to move closer. If you are somewhere in between, okay, so you build, I mean, if we speak in terms of the Gauss's law, then you just build an imaginary sphere, the blue one that you call Gaussian surface, in the shape of a sphere. And then you do the Gauss's law and everything. But anyway, at the end, E, let me call this the E in the middle. You're going to get back the Coulomb's law expression, the K, the charge included in this Gaussian surface. And it's going to be just now negative Q. You guys with me? Because once you are looking at the blue sphere, the plus 3Q is already outside. So those plus 3Q will be excluded from the charge enclosed inside your Gaussian surface. Only negative Q is still inside. So you only include this portion of the charge. Divided by, you can call it R. So this is just a different R. I mean, you can think of R as like a variable. You're going from outside and R is getting smaller and smaller and smaller. So that's it. So over here, you're going to get negative Q over R squared. But the reason I put negative Q over here, just to sort of give you an idea that electric field at this portion will point into the center, I mean, point towards the center of the spheres. Yeah. So the electric field outside is pointing outward. Electric field in between in the middle region that will point from positive to negative, which makes sense. You would expect that this one looks like there'll be electric field going in this direction right there. Does that make sense? Okay, so let's give you an idea. But then when you go outside, then electric field start to fall down, but it's point outward like that. There you go, something like that. All right. Okay, very good. And then now, the last one, if you are in here, somewhere inside the inner sphere, let me call this E inside, you can guess now, then there's nothing left. Because once your Gaussian sphere is smaller than the inner sphere, this Gaussian surface won't include any charge in it. So there won't be any charge in it. So the Gaussian law say you won't get any electric field as well. So that will be 0. Done. Okay, cool. Woohoo. All right. Sound effect is back. Okay. All right. In the day that the sound, the notebook and everything so bad, I still want to put the sound effect on. All right, guys. So I hope that's complete all the questions about the problem now. Okay. Why the mid negative Q again? Oh, okay. Because, okay, if you look here, your Gaussian sphere is here. Let me highlight here. Here, this is your Gaussian sphere right there. Right, this is your Gaussian surface, and the charge that is in it, only that negative Q here. Okay, let me highlight here. Yeah, this is only the charge that will be within that Gaussian sphere that I highlighted in blue. Does that make sense now? Okay. So you only include the negative Q in the expression of the Gauss's law. Okay, the positive Q, you can just let it go. Okay, so let me highlight that yellow right there. That's positive Q right there. It's outside. Okay. All right. So once again, you guys asked very good questions here. So these are going to rhyme really well with the question in the exam. Very good. Very good. All right. I think that completes every questions from the set 9. Okay. All right. So we have one more from problem 10. Okay. Let's look at 10. Set 10. Okay. And it's a problem number 4, I think. Okay, let me pull up that problem first. There you go. And you look at the problem number 7. I'm sorry. Okay, 10-7. Okay, here we go. All right. So you have the question about Kirchhoff rule. Okay. Oh, what this problem is? This is 9- what? Sorry. Oh, my brain is not functioning. Okay. Oh, this one is 7 as well. Okay. So that's good. All right. Okay. There you go. So let's do 10-7. Calculate the power delivered to each resistor shown in the figure. All right. So this problem is the same as the question that asks you to figure out the current through each resistor. Same thing. Okay. But instead of asking you like, hey, what is the current through each resistor, we just ask you to calculate the power. But it's no big deal because the power is just I square R or V square over R. Okay, depends on what kind of information you know, or IV. Okay, so the problem goes back to finding out what is the current through each resistor. That's all. Okay, so let's try that. So once again, you ask good question, because of course I will have one question about the Kirchhoff's rule here for you to sort of, try those Kirchhoff's rule techniques and all this stuff. There you go. All right. Oh, that's bad. There you go. Alrighty. All right, let me put all the numbers in. 2 ohms, 4 ohms, 4 ohms, 20 volts, 2 ohms. All right. So once you sort of get that, so let me use this as a review question. Okay. How you figure out the electric field throughout each one of these. From the look of this one, actually, you might not even need like a Kirchhoff's rule if you don't want to. But that's okay. Kirchhoff's rule, yeah. Okay. All right. First thing first. Because these 4 and 4, you can see that this is a simple one. You can use like a techniques that you can find equivalent resistance. Okay. Due to these two are connected in a parallel fashion. You can see that the 2 ends are connected and the bottom 2 are connected. So you can actually reduce this one down into a single resistor. So let's do that first. Okay, so that's 2 ohms still up there. And then I can just reduce this into just a single resistor left. There you go. 2 ohms here, 2 ohms there, 50 volt here. So how much do I put here? So I thought we could not. Yes, you can. Or maybe that's why you have a question, right? Yes, you can. Otherwise, then if you want to like do the Kirchhoff's rule straight out, then you're gonna have like too many loops for you to solve, even though you're gonna end up with the same answers. However, when you have more loops, then you have more unknowns, then you're gonna have like a bigger system of equations to solve, and that's sort of like, not good. So over here, you can, all right, if I say this, so you should be in a good shape now. So those 4 ohms that connected in parallel, this is the 4 ohms and 4 ohms. You can reduce this one down into a single one using 1 over sigma r equal to 1 over 4 plus 1 over 4, which is 2 over 4. So sigma r is 2. So that means it's 2 ohms here. There. Does that make sense? Okay. All right. Now with this, then you can just doing the Kirchhoff's rule just like you did now. Okay. You can start with identifying straight portion of your circuits. There you go. And then next step, you can imagine that each portion has its own currents. I just put them up, all the way up. All right. And then you look at a junction and start with the junction rule. So in this case, because I just like, put them all into the junction that looks like all in, the sum of the in must be equal to out. So that it must be equal to, that's my equation number 1 right there. And now the rest, it's going to be up to you. You just pick a loop. For example, I can do the left loop over here. So let me highlight this one. That's my left loop over here. All right. And I'm going to do this in a clockwise manner. I can start from upper left corner. And I'm going to walk clockwise among those 4 blue dots right there. Or actually, let me do like labeling, just like what we did in class. A, B, C, D, E, F. All right. So what I'm going to do is, let's look at the loop A, B, E, F, A, the left loop. Okay. And now you start using the Kirchhoff's loop rule. Starting from the upper left, keep walking. Okay. Let me use a red color here. I see the 2 ohms with the current I1 flowing. So I'm going from the high potential to a lower one. So the potential change is going to be negative I1 times 2, V equal to IR. Keep walking. Turn. Now I see another 2 ohms with the I2 going against me. When it's going against me, I know that I'm going up the stream. I'm going uphill. I'm going to a higher potential. So it's going to be positive I2 times 2. Keep walking. Nothing happened. Turn. Nothing happened. Now I'm hitting the negative ends of the battery. I'm jumping from negative to the positive. So I'm going uphill again. So the potential difference is going to be positive 50 volt. And I'm keep walking. Now I arrive back at A. This summation will give you 0. That's my second equation right there. Cool. All right. And then you can just pick one more. Let me do another loop. Let's do the left loop, shall we? Just change of the mood here. So I'm going to look at the loop. Let's maybe start from the E. E, D, C, B, E. Here we go. All right. Start from lower left corner. I'm just walking counterclockwise. Keep walking. I see 2 ohms with the I3 flowing in the same direction. So when I'm going in the same direction as the current flow, I'm going in the lower potential. So it's going to be negative I3 times 2. Keep going. Nothing happens. Nothing happened. I hit the positive ends of the battery. So it's going to be positive. I'm jumping from positive down to the negative one. I'm going to a lower potential, and it's going to be negative 20 volts. Keep going. Nothing happened. Nothing happened. Turn. Nothing happened. Turn. Now I'm hitting 2 ohms again with the current I2 going against me. When it's going against me, it means I'm moving uphill. I'm moving up higher in the potential. So it's going to be positive I2 times 2. I keep walking. I am arrived at my initial starting point. So everything must sum up to 0. That's my third equation. Done, guys. Okay. And then I can solve everything about the current flow. Well, Ajahn, what about the original split that you did, that you sort of, merged them into a single R? So no big deal. The easiness of this problem is just you sharing the same amounts of current among these 2 resistors because you're having the same resistance. So that's why once you figure out the I1, I2, and I3, actually that I2 over there will be split among this half and half. You guys with me? Does that make sense? All right. And that's allow you to figure out what should be the currents that passing through the 4 ohms resistor. And that's it. You done. Okay. Cool. All right. So just please make sure that you allowed to do like a resistance reduction or finding equivalent resistance. No problem. Right. Don't have to sort of like just only rely on Kirchhoff's rule. If part of the circuits can be reduced or can be sort of like put in the easier form, then you are allowed to do that every time. Yes. Cool. All right. So far, so good. Am I answering all of the questions you had? Whew. All right. This is fun. Oh, yeah. So I hope it's not too hard in terms of the material, of course. Like the final exam is supposed to be okay, I hope. All right. So any further questions, guys? All right. If not, then once again, I will release the no, we don't do RC circuits, right? Correct. Right. So we're gonna end everything just on the Kirchhoff's rule. Yes. So I will release the exam paper tomorrow at 8 o'clock. All right. So you have 12 hours to do. All right. So you have until 8 p.m. to submit your work, and that's
how many questions going to be?
I'm not so sure yet, but I think it's about the same, about 8 to 10. Shouldn't be more than that. Yeah. Okay. And then during that time, now I have time to sort of grade your thing, and then I'll release the scores along with it. All right. That will be good. It's going to be weird exam. Like, why are you examining and you do the exam, then I'm doing my grading as well. That's really bad. All right, guys. Thank you so much for stopping by today. And I hope you, learn something from the course, I guess. Yeah. And then I will I will be around to answer your question tomorrow. If you have any question, you can drop me a question through the line group if you like. I think maybe that's easier, right? Or if you like, you can just type in the Google Classroom and it will come in the form of an email. So maybe line group will be a little bit better, right? In that way, especially if some questions, your friends supposed to know as well. So asking in a line group, then will sort of like an announcement in a way. All right, guys. So if you have no more question, then just wish you guys good luck tomorrow, and then I'll see you around. I think yes. Go ahead. Right, but for those of you that's done with the question, then thank you so much for stopping by. I'll see you tomorrow. We still have question about homework later. Yeah. Just drop the question. I'll check the line group sometime to time. Yeah, so the exam, like what we decided, so overall the exam will go, what is that, 35. So each exam will worth 35, 35, 35. So that means you have 105. And then I have 15 points from the homework. So that's why we have 120. That's mean, sort of like exploded score. And then we do the grading using the MUIC grading scheme, evaluation scheme. So A will be above 90, something like that. All right. Or actually, yeah, I don't remember exactly, but it could be like 40, 40, 40. And the homework is 10, right? I think we have total of 130. Okay, I think that make more sense. Yeah. All right. So it's 40, 40, 40, and then plus 10 with the homework. So it means if you aced 2 of the exams with the homework, then you already got A. You can just skip total 1 exam, something like that. Yeah. All right. So I hope that helps. Okay. Thank you. Okay, that's good. Yes, question, please. Yes.
Yeah. So I got the question from about what's called the gas law. Okay.
Yeah.
And related to. So my question is that there will just be the normal shape, right?
The
There have
normal
no
shape of what?
complication. I mean, about the issue passing of closed and closed object. That
Uh-huh.
question, that kind of question. Yeah. I was just wondering, will we just parallel unified electric field with no, you know,
Can you summarize your question again?
I just wondering if that we will have a non-parallel
Uh-huh.
electric field from a charge example
Uh-huh.
passing through an enclosed object and we have to calculate that. We're not going to have that.
I don't think it's gonna be that complicated.
Oh, okay. So
I think it's
going to be
either
easy.
uniform, or if it's
You know.
non-uniform, it must come out like a spherical symmetry or something like that. That's what we learned, right?
Oh,
I don't think we're gonna try you to do like some weird electric field lines and then come up with the question of asking like what is a flux through this through that. I don't think it's beyond the scope that we are doing. So don't worry about that. I don't think. No, I don't think we have that kind of question. No.
okay.
Yeah.
Cool.
Yeah. Oh, that's a question. Okay. Okay. That's some concern. Yeah, you're right. Okay. Oh, it's correct. Yeah, all right. Okay. Just keep typing wrong. Okay. Yes. All right. All right. So for the homework, just take care of the one that had the submission. Correct. Yes. All right. Should be good. ครับผม Oh, okay. Yeah, go ahead. Question. Oh, okay.
Yeah,
Yes.
yeah. So I want everyone else to go first. Don't have any question.
Not related to physics.
Yeah.
I
You're
think
not
I think
related
it's
to
time
physics.
now. I think everyone is just leaving now already. Yeah, you can ask.
Okay.
All right, let me stop recording first. I think that's done. Okay.